All right, so I'm Avi, and I will talk about our experiences last year, what we've worked on, and what we're going to work on for the next year for ScyllaDB. About me, so in the distant past, I was the author and the maintainer of the KVM hypervisor, and now I'm the CTO of ScyllaDB. And let's start. We'll start by talking about large partitions. If you've used Cassandra and even Scylla, then you know that they're problematic, and I'll discuss why and what we're doing to mitigate those problems. So what are partitions? What are large partitions? If you start from a table, a ScyllaDB table, then it's composed of partitions. You index the table with a partition key, and you get to a partition. And then you can further index the partition with a clustering key and get to a row. And the row is what you're really interested in. A row is a unit of data. What's important about the partition is that it's the unit of distribution. A partition is always on the same node. So when you add nodes and you're streaming data from one node to the other, the partition moves as a whole. And that allows the partition to be ordered. You can select ranges of row within the partition, and you can get a little bit more value out of that. So it's important to remember the distinction. And what we've been doing is looking at changing Scylla from being partition-oriented towards being war-oriented. In partition orientation, a partition is a basic managed unit. When you access something, you read the entire partition into memory, and then you slice it up to look for the rows you're interested in, and you return those. And of course, if everything is partition-oriented, then when you have a large partition, you get hiccups. You need to load a large amount of data into memory and then access it, and that causes large delays. Whereas if you're row-oriented, then everything you can do with the data, you can be done at the row level. You only need to read a single row into memory or write a single row. And if the partition is large, then there is no problem with that because it remains on disk and you don't need to process it. So where are the problems with large partitions? There are many. For example, one of the biggest problems is with the file format that we share with Cassandra. And the way that indexing works is that you start with a summary, which is a file that is resident in memory, and you use the partition key to locate a section in the index. And you have one section in the index per partition. And from then on, you use the section in the index to locate the particular row. And the problem is that when the partition is large and has a large amount of rows, then the row index within the index is itself very large. So even though you don't need to read the entire partition into memory, you still need to read the large section of the index into memory in order to locate your row. So if the partition is particularly large, you get that hiccup from reading the index. So with the Cassandra 3 file format, they solved that particular problem by adding an index to the index. So when the index of a partition is particularly large, it has a small index in front that allows you to search that index without loading all of it into memory. And that solves that problem, but not always. If the partition is really large, then even that index can be pretty large, and you have those hiccups again. So how do you solve that problem? So fortunately, there have been like 50 years of research in that area, and the standard solution is the btree. What's interesting about the btree is that it's self-balancing. The number, instead of having just 2 levels, like the summary and then the index, or 3 levels, like in the Cassandra 3 file format, you have an infinite number of levels, as many as you need. If you have a large number of rows, then you get a larger number of levels, and you can index your data directly. You start from the top, select the intermediate node, go down to the last level node, and then you go directly to your data. But what's another aspect of this is that instead of having an equal way to access, instead of having unequal ways to access partitions and rows, they're all equal. So if you're accessing a row in a small partition in this model, you traverse 3 nodes. But if you look at how a large partition is stored, you also need to access just 3 nodes because the partition takes up a section in the intermediate levels instead of being at the last level. And that gives you fast access to a row in a large partition. Essentially, it's the same latency as access to a small partition in the same table. Again, on the theme of partition versus row orientation is repair. Repair is a process that happens when you need to reconcile data between different nodes. They can get out of synchronization for different reasons. For example, a node was down for an amount of time, so it wasn't able to accept new writes. The node is now back up, and we want to make sure that it has all of the latest data. So you perform a repair operation. And the current repair operation, it has partition granularity. It even has greater than partition granularity. We move 100 partitions at a time. So if you have a mismatch in just one row of those 100 partitions, then you need to synchronize all of that data, all of those 100 partitions. And if you have different mismatches between different nodes, then you need to move all of that data from one node to the other. And we're now working on row-oriented repair, which eliminates those problems. Instead of having partition granularity, you can repair a single row and detect the mismatch in just that row and transfer it to repair the data. So row orientation is a long-term effort. The basic support was added to version 1.3, which is maybe a year old. We've just added support to the cache in 2.0, which was released a few weeks ago. And that's not complete. We're enhancing that support in 2.1, which will be released soon. The repair, which I described, will gain this row orientation in 2.3, and the SS table index will move to a btree format a little later. Something else we're working on is increasing the disk to memory ratio. And I'll explain what I mean by that. So ScyllaDB is part of the ecosystem that's called big data. You have large amounts of data. You saw in the previous presentation 150 terabytes of data under management, and there are even larger clusters. And in many databases, you usually have about a terabyte of data, maybe a few terabytes of data per node. And you need a lot of memory to handle those disks. In ScyllaDB, you can have nodes with 30 terabytes of data. And we require about 30 to 1 disk to memory ratio. So if you have 15 terabytes of data, you will need 500 gigabytes of RAM on your machine. It really depends on the workload, but that's a general rule of thumb. But our goal is to go even higher than that. We want to go to about 100 to 1 ratio between the disk space under management and the RAM in your nodes. And why that? When you have larger nodes, then your clusters are smaller. And that means that they're easier to administer and they are cheaper. You have SSDs today that deliver hundreds of thousands of I/O operations per second. And that means that you don't need to rely on the data being cached because the disks are fast enough to supply that throughput by themselves. And if you want to rely on the disk, then you don't need that much memory. And you have nodes these days with 10 gigabits per second. That's almost standard. And 20 gigabits per second are also becoming widely available, and even 40 gigabits per second. And you want to take advantage of those by utilizing all of the hardware. And again, that means large nodes. And the hardware manufacturers also agree, and it's pretty common today to have 32 cores per node, and even larger machines are becoming commonly available. What are the challenges with having a large amount of storage per disk? So the first one is having memory resident metadata. And in the context of ScyllaDB and SS tables, those are the compression info.db files that hold metadata about compressed blocks. They allow Scylla to locate where a particular compressed block is located and what's its size. And of course, you want to use compression in order to reduce your storage costs. SummaryDB is the first level of the index that is used to locate partitions. So again, it is memory resident in order to reduce latency. And filter.db is holds a Bloom filter that is used to quickly figure out whether an SS table holds a particular partition or perhaps it does not, and then we don't even need to read the index and read the data. So that's used to increase throughput and reduce latency. So all of those files are memory resident, and that means that your memory must be large enough to hold them and also to leave memory for the rest of the system, for the cache, for the metadata, enough to run. So how are we solving these problems? For compression info.db, we've applied compression to that file, and we're able to achieve about a 3x improvement. So that file takes a lot less memory. Another thing you can do in pre 2.1 is to increase the chunk size. That reduces your efficiency somewhat, but it might be the right trade-off for you if your throughput requirements are not so high. And we plan to switch to cell-level compression, which would completely eliminate the need for that file. So you would no longer have that file. It would be, it's not a 3x and infinity x compression. For filter.db, that file usually grows for tables with many small partitions, because each partition takes a few bits in that file. So if the partitions are small and you have a large number of them, then you need a lot of bits, and that file grows. And the plan is to apply automatic sampling for that file. So if we detect that it's growing too large, we sample it. That reduces its selectivity, so it's no longer as efficient, and we have to go more to disk. But it allows you to have larger storage under management for a given amount of system memory. And last, summary.db. So already in 2.1, we've done automatic sampling so that the file, we make that file smaller at the expense of bandwidth if we detect that it's growing too large. And the replacement of the index with a btree will automatically eliminate it, so it will also be gone. So managing more disk, adding more disk is one way to increase the data under management, but another way is to make it more efficient, to make the better utilization of the disk space that you have. Right now, you need about 50% of free space on your disks in order to have room for compaction. So compaction is a process that reads all of the data in the system, merges it together, and spits out a new file containing that data. And by its nature, it temporarily doubles the amount of data that the system uses. So you need 50% free disk space to have some room for that operation. And what we're doing to improve that is having a new compaction strategy that has a temporary name, hybrid compaction strategy, that will be reduce the amount of temporary space needed, and you will be able to store, to have smaller space reserves and larger utilization of your disks. And we will also introduce logic to take into account the amount of free disk space so that we can start the compaction earlier in order to expire data that is under TTL, that has a time to live, and therefore reduce the chances of running out of space. And there will be a presentation by Nadav about compaction strategies that will also touch this issue. Handling node restarts. So when you're doing a benchmark for a database, it's important to not only check it under normal operation when everything is peachy, everything is running well. You also need to test it under failure scenarios. What happens when a node goes down? What happens when the network goes down. And one of those issues is that when a node goes down, the other nodes take its place, and they should have some spare capacity in order to sustain your load. But when it comes back with an empty cache. And now it suddenly has to satisfy all of your requests from disk. Some disks are fast enough to do that, and if that's the case, then you're fine. But some disks are not so fast, and you will start to see a higher latency. As you can see in the blue line in the graph, you have the high impact of a node being restarted towards the beginning of the graph. So what we do is we take into account the temperature of the cache or the hit rate of the cache, and when the cache is empty, as happens when a node is restarted, we know that it will not be able to sustain the same throughput and with the same latency. So we only feed it a smaller number of requests per second, and we gradually increase the rate at which that node serves request, and we measure the increasing cache hit rate and keep increasing the load to that node until it is ready to sustain an equal share, and then its cache is fully warmed up, and you can see that in the green line that the impact on latency due to a node restart is much smaller, and there will be a full presentation on that by Gleb, which you should all attend. Monitoring is another area where we made a lot of strides. So we started with collectd and graphite, and that was pretty hard to set up. You had to configure a lot of things, and both on the node and on the monitoring system. It was hard to use. There were no preset dashboards, so you would have to know exactly which metric you were looking for. And it was slow and clunky. There was no auto refresh in that, so it was pretty annoying. Recently we switched to Prometheus and Grafana. Those of you who use ScyllaDB will know that it's a completely different. It's very smooth, much easier to use, very pretty, and we supplied the ability in the dashboards to have to drill down. So you can look at the cluster level. You can select. You can zoom into a particular node. You can zoom into a particular core within a node and see a lot of. You can see everything that is happening and see that if anything is not according to spec. Another thing that you can do with it is add alerts so that it will notify you if something is happening. For example, if you're starting to run out of disk space, or if CPU utilization is too high, you can have Prometheus alert you. And we're continuing to improve our monitoring. We're also open to additional monitoring tools, so we will expand our support in that area too. There will be a talk by Zach about monitoring, so if you're interested in that area, I recommend going to that talk. Indexing. So ScyllaDB and a lot of NoSQL database really force you to have one major way to access your data, and that is using the partition key and the clustering key. You use them to access the data, but often it is not enough. A very common example is having a table of user profiles, and you access a profile but a user ID. But what happens when you don't have the user ID? You have just, say, an email, a different identifier like the email address. Then you need an index to, instead of converting the user ID to the email and the rest of the profile, you take the email and convert it to the user ID. And for that, you need an index. So we've added the Materialized views, which is an efficient way to do this reverse lookup. And that's available under experimental mode in 2.0, and will soon be out of experimental mode. And we're also adding secondary indexing that do that transparently. So instead of having to create the Materialized view yourself, you just specify that you want an index on a particular column, and that will come in 2.2 or perhaps 2.3. And there will be talks both on Materialized views and on secondary indexing. compaction strategies, I've already mentioned them a little bit. A compaction strategy roughly corresponds to a query pattern. So if you have like a general purpose a query pattern that doesn't fit into anything else, you're using a size-tier compaction strategy, which is basically a fit-all. But if you have different types of query patterns, you can use a more specialized compaction strategy in order to get better performance, better latency, better throughput. So if you're doing mostly reads, then leveled compaction strategy will reduce the amount of disk access that you need to do for a particular read. It comes at an expense. It means that you need to do more, writes become more expensive. So if you're having a read-intensive use case and not so many writes, then that trade-off is good for you. It also comes with an advantage that the disk space is lower, so you need less free disk space reserves. Date here is, and also a time window, are examples for time series use cases where we have data coming in that is tagged with a timestamp, with the current timestamp, so it's always increasing. And Scylla is able to take advantage of this property, of this monotonically increasing timestamp, in order to optimize the layout of the data and improve your queries. So if you're having a time series sort of use case, use the date here, which was available since 1.3, and you can use a time window when version 2.1 comes out, which should be real soon. And again, you can see in the DAV's talk for more details about that. An additional compaction strategy we're working on is the hybrid compaction strategy. So it does a sort of a mix between leveled compaction and size tier. It tries to take the advantages from both. So the advantage from leveled, that it requires fewer disk space reserve, so you can use more of your disk. And the advantage from size tier is that it works well for both read-intensive and write-intensive loads, or mixed read-write loads. So that gives you the best of both worlds, and we're looking forward to that. Okay, let's just talking about the database is not enough. Also important is the ecosystem around it. So let's take a look about that. So the most important thing for a database is having the ability to access it, and you do that via drivers. And we have drivers for the most common languages. Many of them were inherited from via our Cassandra compatibility, but also some are now starting to target Scylla directly, not just via compatibility. There are going to be 2 talks about drivers. A GoSQL talk by Chris, who is the author of that driver, and a talk about the GoSQL-X, which is a sort of object relational mapper on top of that driver by Michal. There are also, in the big data area, layered offerings. So these allow you to add additional value on top of the database. Things like KeresDB, which adds a time series, or Spark and Presto, which allow you to do analytics on top of the database. And adding graph capabilities with Janus Graph. And there are going to be 3 separate talks on these areas. So if you want to do things on top of the database and not just access it directly, those are the talks to go to. Another thing that's becoming popular recently is the database as a service. Not everyone wants to operate the database themselves. They want to pay someone to operate the database for them, and that gives you some more peace of mind and less hassle. So already there are 2 services that provide database as a service with ScyllaDB. So Compose is one, and InstaCluster is another. And soon there will be a few more. So Samsung will be providing and talking about in their talk about database as a service, and also we will have our own offering in the future. The management console for people who do operate their own database, but don't want to use the command line. They want a good console that coordinates all of the operations. We are building a management console that allows you to have a single pane of glass, an enterprise feature for better control of the database. And there will be an Ignite talk about the beginning of that tomorrow. Orchestration, very large organizations have moved from managing individual VMs or individual servers independently into having a scheduler, a global scheduler to manage all of the nodes that they have. And there are two competitors here, mostly Mesos and Kubernetes. We will be adding support for those in order to facilitate the deployment if you're running a large Kubernetes cluster or Mesos. And lastly, there's debugging tools. So this slide shows Wireshark decoding the native protocol. And with this, you can debug low-level details and see exactly what's passing into the cluster. And it shows you exactly what the query is running and what the results are, and all of the details about the times, the IP addresses, and the sizes of the packets. So you can really drill down into very low level to gain insight about what's happening. And lastly, there is Seastar, which is the engine behind the ScyllaDB, and we're starting to see adoption of that as well. So there is a Smurf, which Alex will talk about. We'll talk about his usage of Seastar for building a log broker, and Pedis, which is a re-implementation of Redis in the same way that we re-implemented Cassandra on top of Seastar. We have the re-implementation of Redis on top of Seastar to make use of large multi-core machines and the really fast performance that the Seastar gives you. Since we started as a Cassandra-compatible database, originally, most of the ecosystem was targeting Scylla only as a side effect of targeting Cassandra. So you would have systems like Spark being adapted to be compatible with Cassandra, and as a side effect, they were compatible with Scylla. But we are starting to see that this is changing. We are now seeing a project that dual target both Cassandra and Scylla. And that means that it's not just a side effect of compatibility. They're also testing on Scylla. We're also seeing a project that start by targeting Scylla and only have Cassandra as a side effect. And also Seastar, which is really Scylla specific. So you can see that Scylla is starting to have more weight in the ecosystem. It's not just riding on the Cassandra coattails now. All right, I'd like to talk about design as an investment. So when you use a database, you make an investment. You have to learn it. You have to code to it. You have to operate it. It means hardware expense, and it means sometimes paying for support. But it also means that you make a different type of investment, and that is a design investment. In the case of a NoSQL database like ScyllaDB, it means that you need to pay attention to how the data is sharded. You have to make sure your partitions are done right, and you have to design your data model around your queries. So that's a significant investment. And what Scylla gives you here is that you get more for your investment. In Cassandra or in other databases, when you select your partitioning model, you allow the database to partition the data among the nodes. So that's what it buys you. In Scylla, it buys you more because it allows the database to also partition the data among the cores. And this way, it gives you even more performance for the same design effort. So you have to undergo this effort. It's a significant switch from the relational model. But with Scylla, you get more for that effort. Also, when you're using a distributed database, you have to use parallelism. You have many nodes, and you have to provide load for those nodes by having multiple connections and multiple parallel requests. And with Scylla, again, you get more for that effort because if you've designed your application to have a lot of parallelism, Scylla delivers more from that investment because it is able to parallelize the work not only across nodes, but also across all of the cores in the system. So again, you get more value out of that design effort. Okay, I'd like to talk about migrations. As we started as a Cassandra rewrite, obviously, naturally, we saw a lot of migrations from Cassandra, but recently we've started seeing migrations from different databases. So we've seen migrations from Mongo, Elasticsearch, which we'll see a talk about, Redis and MySQL, and I think even more. And they're all migrating to Scylla. They recognize that the performance and the latency advantages are pretty high. And there will be a talk about Sasha Sicular about how to do those migrations with no downtime. So you don't need to take your service down in order to do the migration. A lot of people don't like that. Scylla is, we're proud to be on the leading edge of technology. So right now we're running on 4 CPU architectures, on x86 of course, ARM, Power, and systemz. And we're able to take advantage of the biggest machines out there. And you've all heard about the demise of Moore's Law. So machines are not getting faster, but they're still getting bigger. So each year we're getting servers with more and more cores, more and more threads, and you need a system like ScyllaDB in order to really be able to take advantage of those new and larger machines. It's not just bigger machines, it's also bigger storage, and faster storage. There are the new storage technologies that are coming online, Intel Optane and Samsung ZSSD, and there will be 2 talks about the integration of Scylla with those new storage technologies. They're going to be very interesting. So to summary, Scylla is a database with momentum, and you can see that by just how much bigger the summit is compared to last year, but also you can see how the many improvements that were made last year, and there's still a huge amount of work that needs to be done, but I think that we already established as the performance leader, and when you think about fast NoSQL, ScyllaDB should be the first word that comes into your mind. So thanks, and if there are any questions, I'll be happy to take them, unless my eyes get burned out by the floodlights.